Okay, so today we talk about the hierarchy problem. So the hierarchy problem, in short, is about the stabilization of the electroweak scale or the Higgs mass under radiative or loop corrections. So that's the definition. What it means is the following: if there is a new physics scale lambda, which interacts with the standard model. It could be directly some new particles coupled directly to the standard model, or some new particles coupled to something which is coupled to standard model. So it could even be indirectly. Then the correction to the Higgs mass from loops or radiative corrections, they are proportional to the square of the new physics scale. Okay. So what does this mean? In particular, if new physics is rather heavy, okay, so if the scale is very large, the energy scale, much bigger than the mass of the Higgs. So if new physics is far away from the electroweak scale, then we are talking about fine-tuning. In particular, we have observed the Higgs mass to be about 100 GeV, and that there are these, when we want to compute in a model beyond the standard model, we want to compute the Higgs mass, we have these radiative corrections, which goes as the square of the new physics scale. So there should be some other contributions that you have to finely tune in order to cancel these big radiative corrections and stay with a small observed mass. So for example, let's assume that the new physics comes at MP, which is the Planck mass. The Planck mass has to do with the gravity. It's the Newton constant is inversely proportional to the Planck mass squared in pretty much the same way as the Fermi constant is proportional to the inverse 1 over v squared, where v is the electroweak scale. So this has to do with the completion of gravity. Okay, so let's assume that there is nothing up to this scale, and that the new physics comes there, perhaps let's say perhaps a string theory. So this should be M Planck is related to the string coupling and the string mass. So now we want to compute the observed Higgs mass. The Higgs mass is way smaller than the Planck mass. So the Planck mass is 10 to 19 GeV, while the Higgs mass is 100 GeV. So in Planck units, Higgs mass is this number which has 0 and 32 zeros and 1. And the way you get this number, so you have radiative corrections, which are this part here, which are proportional roughly to M Planck squared. Then you have to fine tune the theory parameter. Okay, you have to fine tune it to 32 digits, which looks a bit absurd. I mean, looks unnatural. And this is why this problem is typically referred to as naturalness problem. Okay. So what the electroweak hierarchy problem suggests is that there is probably new physics not far away from the TeV scale. In fact, I dare to say that this is one of the best motivations we have for the TeV scale physics, for the TeV scale new physics, where our Large Hadron Collider is currently operating. All right. So the literature for today's talk is our lecture notes by Matthew McCall, which I really recommend to read. There is also a TASI lecture on non-SUSY BSM by Chaba and collaborators. And some examples are taken from the standard QFT textbooks like Schwartz and Peskin and Schroeder. So I will try to go really from the basics. So the hierarchy problem has to do with the computation of the mass of elementary scalar field. So I will go, and it's really a theoretical issue. It has to do something with a neat some neat properties in relations in quantum field theory. So I will go slowly, giving you some basic introduction in this subject. Please, if there are any questions, stop me at any point. So the first the first result in quantum field theory, which I would like to remind you of, is the Cullen-Lehman spectral representation. This is a non-perturbative result for the two-point correlation function. It tells us the form of the two-point correlator of a field using simply some basic axiomatic principles of quantum field theory, such as unitarity, positive norm, and causality. Okay. So what is this form? So here you can see the Fourier transform of the correlator, two-point correlation function, to the momentum space, and it's given as the integral over some variable m, okay? And m is plotted in this, shown in this plot along the horizontal axis of the spectral representation ρ. And ρ has a very interesting form. It's positive everywhere, and it has an interesting interesting structures in terms of poles. For example, it's basically zero all the way from zero going to high energies, and the first thing what happens is that it hits the pole, and this is the pole of the particle associated with this field. Okay, it's a physical. So this thing is a physical thing. It's a what we call the pole mass of the particle. The physical mass is the mass which you measure in the experiment. And then what happens later on at higher energies, you can get corrections to this correlator, which come from branch cut and multi-particle states, etc. Okay, so this pole mass is the first thing that we introduce, and it's what is observed in the experiment. And in particular, the experiments at LHC have measured the Higgs mass to be around 125 GeV. Okay. Now, that is what we measure. That is the observed quantity. But how do we compute the pole mass? How does this computation work if you have some theory, underlying theory, which we represent by Lagrangian? Okay. So, staying within perturbation theory, we can use something which is called the Dyson equation, which organizes the computation. So we have an infinite series. We want to calculate the correlator, which is the full theory propagator. So two-point correlation function, I will call the propagator. So we want the full theory propagator, or in other jargon is to say the dressed propagator. is this an infinite series expansion? So you can use Dyson equation to resum the series to all orders. So in particular, you can see that this is just a geometric series. So you can see if you factor out the free theory propagator, which is this one, you will get this term, which we call the self-energy, and again then the full dressed propagator. And the self-energy is the sum of all one particle irreducible vacuum polarization diagrams. So what are these one particle irreducible diagrams? So these are basically diagrams where with all internal lines, when you draw a diagram, there are these internal lines, which they carry loop momenta. So this has to do with the loops, typically. They carry loop momenta. That definition is equivalent to the definition that if you cut an internal line, that you can separate the graph in two pieces. But the first definition is relevant for us. So any internal line carries a loop momentum. All right, so you can solve this Dyson equation, which is just the sum of this infinite series, and you can get this equation here. So this is the full theory propagator, including interactions, in terms of the free theory propagator, which has a simple form, and then the self-energy. Okay. All right. So let's take an example. So what are we going to do? We always want to compute. This is our main player. It is the self-energy. So we want to compute these self-energy diagrams, which will, which define what the pole mass is. So let's take one example. I'll take a real scalar field, H, which has the following bare Lagrangian. So the bare Lagrangian is written in terms of the bare fields and the bare mass. And also interactions has bare couplings. Then I will do the renormalized perturbation theory, which means I will split the initial Lagrangian in two parts, where the first part will contain renormalized fields and renormalized masses. The difference between bare and renormalized is that the first one, the bare quantities are infinite. So bare quantities are just a bookkeeping tool to deal with divergences, ultraviolet divergences in quantum field theory. So we will split the initial Lagrangian into two parts, and the divergences we will hide in the so-called counter terms. So these are this is the counter term Feynman diagram. Okay, so delta Z and delta M are the counter terms, and they are infinite quantities which you use to get rid of the ultraviolet divergences. Okay. So how do we calculate the self-energy? First of all, there is only one 4-vector in the problem, the momentum 4-vector in the P. So this quantity is depending on the Lorentz scalar P squared. Okay. So it's a function of P squared. P squared is it's a scalar quantity. So is the sum of all these diagrams, which you see here. Okay. So we have to, that come from interactions. And the interactions are shown in this additional part of the Lagrangian, okay, which is shown here. Plus the two counter-term Feynman diagrams, which are these two. So what you can typically do is that the series expansion in p squared. Okay, the series expansion in p squared around some m square. M square is some constant mass. So when you do the expansion, so this is the first term, this is the second term, and so on. The divergences that the ultraviolet divergences would appear only in these two terms. In particular, the constant term, which doesn't depend on p squared, will basically be the divergences from that. The divergence from that term will be reabsorbed into the mass counter term. Okay. While divergence in the second term will be reabsorbed by the wave function renormalization, delta z. So there are two things. One is regularization, which means when you write down your loops and you have an integral over the loop momenta, you will have to introduce this typically will be infinite, these integrals. So your integrals will typically have infinities. So you first have to regulate these integrals, make them finite. And the way you do this is to introduce a regulator, a UV cutoff or a regulator. And this is called regularization. There are many different ways to do regulate your integrals, and this is called regularization scheme. The second thing you do is to do renormalization. Renormalization means to absorb infinities into your counter terms. Remember, counter terms are these bookkeeping parameters that come from the bare mass, bare coupling, wave function, bare fields, and so they also contribute through these counter term diagrams. So the idea of renormalization is to absorb the infinities into these counter terms such a way that the self-energy does not depend on the regulator. Okay, that's renormalization. It will be regulator-free, the self-energy, while delta Z and delta M will depend on the regulator. So also there are different renormalization schemes. The two most common renormalization schemes used in the literature are on-shell renormalization and MS-bar renormalization. For example, MS-bar scheme relies on dimensional regularization. Okay, so dimensional regularization means to calculate your integrals in d dimensions where d is less than 4, and this would regulate your integral. It's a specific way to make the integral finite. And the on-shell renormalization, you can use arbitrary regularization for this one, but it has conditions. In particular, the conditions are the following. So if you remember this expansion, you require that the first term is 0 and that the derivative is 0. If the first term and the derivatives are 0, and this will fix your counter terms, delta M and delta Z. This requirement fixes the counter term. Remember, mH is the pole mass. What you will get is that your propagator, let's go somewhere for here. So your propagator will have this first term of your propagator will have a residue equal 1, and this m will really be the Paul mass. So you are matching the Cullen-Lehman spectral representation, the first term in this representation. So this is why it's called on shell. So you are identifying this parameter with the Paul mass. In MS bar, this MH, which is the renormalized mass in the Lagrangian, is not the physical Paul mass. Remember, MH is the renormalized parameter in the Lagrangian. In on-shell renormalization, it is the Paul mass. In MS bar, it's not the Paul mass. The Paul mass will be some expression. It will be MH, and then there will be some other contributions to it. So from this discussion, you see that there is quite a bit of arbitrariness. In particular, it's very important to understand that the parameters in the Lagrangian, couplings, the parameter in Lagrangian m square h square, m is the coupling. We call it mass, but effectively it's just the coupling. Okay, it's only in some specific, for example, in on-shell renormalization, you can identify that with the Paul mass. Also, the fields you can in Lagrangian in the Lagrangian you can do field redefinitions, and you can get terms in the Lagrangian that look rather different from your initial Lagrangian, but yet they represent the same physics. In particular, they will lead to the same scattering amplitudes, etc. So there are many redundancies in the Lagrangian. This is why, talking about the hierarchy problem, I'm saying, okay, so there is the mass term, it receives contribution from different pieces. It's really a theoretical issue of how you're doing your calculation, and you really have to be precise when defining this problem. Okay, so that's what I want to try to do in the next couple of minutes. So I will take a specific interaction of the Higgs field and then try to play games with different regularization schemes to see if this behavior, the quadratic dependence on some regulator, changes or not, and what does this mean? Okay. So I will consider this interaction, Higgs to the 4, where I have the following Feynman vertex for this interaction, 4 Higgses. And I will do a hard cutoff regularization. So at one loop, the correction to the 2-point function. So I want to calculate the self-energy will be the diagram of this type. K is the loop integral. Okay. All right. So this is the loop. So I have the coupling constant for the vertex. 1/2 is the symmetry factor. I have the integral over the loop momenta. And then in this loop, I only have the one propagator. So it has this form. Okay, the propagator of the Higgs field. So to do this loop integral, you just use the standard methods. So since this is in Minkowski space, you first do a Wick rotation to Euclidean momentum variable, and the Wick rotation is shown in this plot. So your initial integral is over the real value of the K0. K0 is zeroth component of the momentum, the time-like component. And then you are rotating it to the vertical one, which is the imaginary. So you're using this relation. So you are going to go to Euclidean signature. And you can do this because the structure of the poles doesn't change. And you also assume that at large K's, at large K, at large momenta, the integral, there is a regulator, so that the integral is finite. Okay. So yes, you change to the Euclidean space, and then this becomes, there is a plus sign here. Okay, so then you can separate your four-dimensional integrals into the surface integral and the radial integral. Okay, this one. By using this substitution here. The surface integral is simple to solve. It's just a numerical factor. The radial integral is, yeah, so this is also a trivial integral. So the hard cutoff means that I am just, so I'm calculating this radial integral from 0 up to some lambda. Where lambda is cutting the high frequency modes of the loop integral. So here you can see that we got really when we calculate this integral. So we have k cube in the numerator, which comes from the change of variables in the integral, and then we have k square in the denominator. So at very large k, this is linear. This goes as k. So when you perform an integral, this will be quadratic in lambda. So this is this quadratic dependence that I promised in the initial, at the beginning of this lecture. So there is a word of caution here. The cutoff, hard cutoff regularization is not really consistent with the assumptions of the weak theorem, but we will suppress this for the moment. Anyways, for the moment, let's ignore this fact. And let's just have a look at this expression. So we calculated this loop, and we got that, so there is a loop factor, okay, 1 over roughly 16 pi squared. There is this coupling constant, and then there is dependence on the regulator, which goes as lambda squared. And then there are these other pieces here, which go as the mass, Higgs mass squared. So these are these quadratic corrections in the cutoff. So you may ask the question, is this a regularization scheme artifact? Remember the discussion that I did and saying that the Lagrangian is full of redundancies. It in fact turns out that the answer is yes. And I will show this in dimensional regularization. However, this lambda we should think about this in terms of effective field theory. So remember that last time we connected, no, in the first lecture, we connected renormalization to effective field theories. We said that the UV divergences had to do with the fact that in the loops, we encountered these high frequency modes, which are related to these very local, try to see what's happening at very short distances where our theory does not hold anymore. So we are, in those modes, we are actually extrapolating our theory beyond the regime of its validity. So this scale should be thought of as the scale where the theory breaks down. Okay, so we need another theory to complete it. Our theory in which we calculate is just the low energy limit of this more complete theory, where the new physics kicks in. Okay. So from this effective field theory perspective, we should expect that the new physics is this lambda will be replaced by new physics, really genuine new physics scale. Okay. So let's try to repeat this exercise in dimensional regularization. Okay. Dimensional regularization means that we are calculating our diagrams in d dimensions. These are space-time dimensions, where d is smaller than 4. Our world is in 4 dimensions, and we are going to less dimensions. There will be this epsilon parameter, and it is actually our regulator. You will see that the loop is finite in less dimensions. So the integral is finite. You can calculate it. So the first, when you do these calculations in DIMREG, you have to massage the Lagrangian a little bit. So now you have to repeat the canonical dimension scaling. Remember that the dimension of the Lagrangian density was 4, but if you go to d dimensions, there is actually d, and everything changes. So you have to figure out the dimension of your coupling. So in particular, the coupling lambda, which was dimensionless before, now picks a dimension, and we are forced, because we are forced to introduce a scale. So we introduce a scale mu simply to compensate for the dimensions of different terms in the Lagrangian, and it's completely arbitrary scale. Some arbitrary scale which is introduced by dimensional regularization. It's an artifact of this. So remember, epsilon is the regulator. It is the thing which regulates the integral, and mu is the arbitrary scale which comes to have a proper dimensions for our coupling constant. All right, so let's do the loop. So we have the coupling constant. We have the integral over k. So we have the propagator. And so this is the solution. So typically when you integrate this stuff, you get gamma functions. Remember, gamma functions, they have simple poles at non-positive integers. What does this mean? So they blow up. They blow up when the argument is a negative integer or 0. So in particular, when you put d equal to 4, we will get gamma of -1. So that's infinity. Or even this integral is very specific in the sense that even d equal 2, if you calculate in 2 dimensions, there is also an infinity. Actually, this quadratic divergence is somehow related to this divergence of gamma function for d equal 2. But our world is not d equal 2. We are in d equal 4, right? So we have to take this limit when epsilon goes to 0. All right, and now I'm just doing some algebraic manipulations here using the properties of the gamma functions. And I'm calculating, so you should be looking at this at the final result. So the final result is shown below this thing. So again, there is a coupling lambda, then there is a loop factor. But notice a huge difference with respect to cutoff regularization. Now the loop integral is not proportional to some, it's actually, it has this proportionality to the Higgs mass squared. So it's not proportional to mu or whatever. Remember, in the cutoff regularization, it was proportional to the lambda squared, the cutoff, the regulator squared. Here it's proportional to the Higgs mass squared. Okay. Other terms in this formula, this is just some numerical number. Sorry, it's just a numerical factor. It's some number. It's a real number. Okay, and then there is this regulator, 2 over epsilon. So 2 over epsilon, when epsilon goes to 0, this blows up. Remember, the self-energy is the sum of the loops plus the counter term piece. So in MS bar scheme, you can hide this divergence. Namely, so if you choose your counter term to be equal to this, okay, then when you sum up the loop plus the counter term diagram, the divergence will cancel, and the self-energy will not depend on epsilon. So simply delta M will cancel with this other piece. But still, there will be other terms. For example, there will be this term here. There will be this term here, left out. mh squared times log of mu squared over mh squared. Anyways, so not to diverge too much from my main point, in dimensional regularization, the correction is proportional to mh squared, and it's not an mh squared, so this is not a huge correction. In dim reg, it seems like this is not a huge correction. And indeed, if you don't have new physics, okay, there is no hierarchy problem. So we did calculation in two regularization schemes. We used hard cutoff, and there was this dependence on lambda square, and we used the dimensional regularization, and there was it was proportional to the Higgs mass squared. So in that setup, there is no tuning, okay. However, the tuning comes when you have new physics. So standard model, if there is nothing above, so if you assume that there is nothing above the electroweak scale, and the standard model is the entire story, which it cannot be. But imagine that for some reason the standard model is the final theory. Then talking about hierarchy problem is not really meaningful. It only becomes meaningful if you have new physics. Okay, so let me show you how this works. So if I have a new field phi, so this is a new field, and in particular, the mass of the particle which is excited by this field is much more than the Higgs mass, and it has this interaction. Now the point is, when you have a new field, in both regularization schemes, you get that the self-energy is proportional to the mass of the heavy particle. I choose this example precisely because the computation is the same. So instead of the Higgs running in the loop, you have this phi field running in the loop. Okay, so the computation is the same. So even in dimensional regularization, this term here will be mass of the heavy guy. Okay, so now the correction, even in the dimensional regularization, will be proportional to the mass of the heavy guy squared. And also here, remember there was this term. There will still be this unphysical, this regulator, but there is this additional term here, which will go as the square of the heavy mass. So this will be, in this example, m phi squared. So in all regularization schemes, the self-energy will receive a correction which is proportional to the square of the mass squared of the new field. So from here you can see that this effect is really physical. So this is hierarchy problem. So you can only talk about it when you have new physics. If you have new physics which is heavy and coupled to the Higgs, then there will be a contribution to its mass, irrespectively how you regularize your integrals. Okay, it doesn't matter how you do it. There will always be a contribution which is proportional to to the mass squared. Are there any questions about this at this point?
I have one.
Yes, please.
How generic is this coupling, this Higgs square times the other new physics particle square? Or is, I mean, as I understand it now, that's really the reason for this dependence on the square of the cutoff, right? Or of the new physics scale. Is that for all proposed new physics models, or is that?
Right, that's a fantastic question. So there will be, so this is just one example which I wanted to use because the loop integral is very simple. But in fact, exactly the same behavior happens if you have, for example, Higgs couplings not to scalar but to fermion, like Yukawa couplings. Mm-hmm. If you couple to the top quark, that's the dominant diagram in the standard model. You have this quadratic dependence on the new physics scale. If you couple to gauge bosons, you also have it. Mm-hmm. It's a quite generic feature. I choose this simple example only because the loop integral was very simple, and you can really see at which point you get the divergence.
Okay.
I will come to this later on.
Thank you.
Yes. Any more questions?
I will answer the question. So let's say we have a very light particle as a dark matter particle, so not at high energy. So that would mean that we do not have a hierarchy problem then at high energies.
So you mean the related to the Higgs?
Yes. So if there's only a very light new particle,
that's correct. But for example, if your light particle is a scalar, then you should be careful about its mass. You should protect its mass from the electroweak scale. If it somehow talks to the standard model, and we know that in standard model there is electroweak scale, and if your guy is very light, and if it's scalar, then you should worry about its the stability of its mass.
Okay, thank you.
Let me first explain what happens if you want to calculate the mass of vectors and fermions. Why is elementary scalar special, and what happens in the case? Sorry, is the elementary scalar special, and what happens for vectors and fermions? Okay, so let me compute the self energy for the massive gauge boson vector. Okay, so the self energy has a dimension. There are these mu nu indices, which are the Lorentz vector indices. It has a canonical dimension of 2. So again, there is one momenta p, and we can start expanding in this momenta p. So there will be a constant term, and then there will be things which are order p square, or perhaps p mu p nu. They come in this additional piece. So this thing, the first term is the constant term. But let's see. The question is, can this term be proportional to lambda square? That's the question. If you go to very high energies, the gauge invariance will be restored. So, for example, imagine there was some spontaneous symmetry breaking. And gauge invariance actually protects the mass of the gauge boson, meaning that in gauge theory, vector bosons are massless. And this term will be contribution to the mass. Okay? So it has to disappear. That is the logic. This term has to disappear, the constant term, when gauge invariance gets restored. And this is only possible if it's proportional to MW squared. So you have to have this MW squared. It's imposed by gauge symmetry. Therefore, the dependence on the cutoff goes in the logarithm. The correction from new physics to the mass of the gauge boson will not suffer from quadratic dependence. Okay. Other way to see this is that in the unbroken phase, imagine you have some U1 gauge boson. Gauge invariance dictates a very specific form for the self energy. which has this form P mu nu minus G mu nu P square. This form is consistent with the word identity. So this is the property of gauge symmetry. And therefore, you pick up two mass dimensions, two canonical mass dimensions, P square. And therefore, this term should be, so the scale lambda can only come in the logarithm, log of lambda square of P square. The conclusion here is that the vector boson is protected by the gauge symmetry. Okay. Let's now take a fermion. So in the case of the fermion, the dimension of the self-energy is 1. Remember that self-energy has the dimension of the inverse propagator, and the dimension of the propagator of the fermion is -1. So again, we have this momenta P. Now we do expansion, so we will have a constant piece, and then there will be a piece linear in P, order and so on, other higher orders in P. Now, what about this constant piece? Can it depend on the scale lambda? This mass term of the fermion field connects left chiral to right chiral fields. It connects left-handed to right-handed. Okay. If you don't have this term, then you have the chiral symmetry. So there is a global symmetry, so-called chiral symmetry, which is U1L, U1R. What does this mean? So you can independently rotate left-handed fields, and this kinetic term will stay the same, and the right-handed fields with the other one. So this will be the symmetry of the Lagrangian. But if you have the mass term, which is this thing here, it will break the chiral symmetry because it connects left-handed to right-handed. So this constant term should not be there when the chiral symmetry is exact. Okay? What does this mean? But this means that when the breaking is proportional to MF. So you have to put MF, the mass of the fermion, which eats up one dimension. And therefore, the scale can come only logarithmically here. So it will not be a power correction, it will be a logarithmic correction. Logarithmic correction is not that problematic for fine-tuning problem. So for example, let's say log of m Planck over m Higgs is 17, okay? But power corrections are problematic. Lambda, so m Planck over m Higgs is 10 to 17, okay? All right, so the chiral symmetry protects the fermions. Fermion mass is protected by the chiral symmetry. What does this mean? So look at this diagram here. If I want to calculate some loop correction to so I have psi left, psi right to the self energy of the fermions, and imagine I have this gauge boson interaction which come from this covariant derivative. So derivative has inside an interaction with some gauge boson field. Okay. So if you follow the chirality line here, this is a chirality conserving interaction, LL, RR. So in order to you need to flip the chirality in this propagator. Okay. And to do so, you have to insert the only thing which breaks the chirality is the mass of the fermion. What does this mean? This means that sigma will be proportional to mass of the fermion. Okay, that's just another way to see it. And since it already has dimension 1, then it can only logarithmically depend on the new physics. Okay. So if there are no questions, I would stop at this point. So can we continue? Are you there?
Yes.
Yes. Yep. All right. So the two examples about the gauge boson and the fermion, which I stated in previous slides, followed something which was first discussed by Hooft, formulated by Hooft. It goes under the name of technical natural. A parameter is technically natural if setting it to 0 would enhance the symmetry. Okay, so the mass parameter, if you set it to 0, it would enhance the symmetry of the Lagrangian, or the symmetry was there. For example, in the fermion example, when we set m to 0, the Lagrangian, you could see this chiral symmetry, enhanced symmetry. And in such case, the renormalization of this parameter, the corrections, radiative corrections to this thing, should go proportional to itself. You can think of this parameter as being a spurion, which breaks a symmetry. So all the breaking of this symmetry should be proportional to the spurion in some way. And therefore, you have a multiplicative renormalization, meaning that higher order terms will come proportional to that, and there is also a loop factor, so they would typically be small. Okay. This is technically natural. For example, the fermion Ukavas that we encountered last time, they are technically natural. Sure, we still don't understand this weird flavor puzzle, but at least it's stable under radiative corrections. I want to show you one example. It's a very strange example from my recent work, where please follow carefully. The fermion masses is tuned. Fermion mass is tuned. It's not. It has this naturalness problem. So it's not protected by symmetry. It's tuned in Hooft sense. So in this model, we were after some. It was about neutrino physics. We wanted to generate some large chirality violating interactions of neutrinos in connection with some dark matter experiments. So we extended the standard model by adding a leptoquark. It's a new particle. This is just an example, S1. And the leptoquark is a particle which couples a quark, in this right-handed B, with a neutrino. Okay? So you have a Y1 coupling, which is the coupling of the right-handed guys, and Y2 is the coupling of the left-handed guys. So it's the same particle coupling left-handed neutrino and the left-handed B quark. So here we are assuming that neutrino is a Dirac, okay? So there is both left-handed component and the right-handed component. But notice one thing, the Dirac mass term of neutrino is not technically natural. So it's not technically natural. Why? If I send it to 0, I do not restore the chiral symmetry, because I still have these interactions which violate the chiral symmetry U1 left of neutrino times U1 right. Because you see, nu right is coupled to B right and S1, and nu left is coupled to B left and S1. You cannot rearrange U1s that you have in this problem to have to protect the mass term of the Dirac, because these interactions are very specific. So what happens? So let's calculate the radiative correction to the Dirac mass term. It is this diagram over here. So in this diagram, you can exchange a leptoquark and a bottom quark. You can put the two couplings. So you can use Y2, which is the coupling of the left-handed guys, and Y1, which is the coupling of the right-handed guys. but if you follow the chirality line here, you see that you have to flip a chirality at some point, but you can do this flip inside the loop. And inside the loop, you have the bottom mass, actually. It's the bottom quark running in the loop. So the correction to the neutrino mass is given by this form. Okay? It's a radiative correction to the neutrino mass. And it's not proportional to the neutrino mass. It's actually proportional to the MB. So it's really a tuning problem. It's the tuning like the tuning for the Higgs. Experimentally, the bottom mass is about 4 GeV, and the neutrino mass is below 0.1 electron volt. So there are 10 to 10, the ratio of this is 10 to 10. 10 orders of magnitude difference. So you have, if you consider the loop factor, you maybe have something like 8 orders of magnitude. The radiative correction overshoots the observed neutrino mass. So there is a large tuning needed. You have to take the 3-level Yukawa and tune it against this contribution. This clearly is not good for our model, okay? We suffered a lot to try to address this issue. But I'm showing you here that in some exotic cases, this is not only the issue of the elementary scalar. Is this example clear? Fantastic. Okay, if there are any questions, please interrupt me. So, okay, let's just recapitulate at this point. So for an elementary scalar, H, you can do NDA. So when you calculate the self-energy, you have the constant term, okay? And then you have the term which goes as p squared. The constant term is the thing which is the mass. And for example, in this interaction which we considered, there was no symmetry protection. If you lift, if you send m to 0, well, in fact, this is not quite right. So to be more precise, let's try to go this way. So when I send m to 0, do I see that symmetry is enhanced? In fact, there is one symmetry which appears, and that symmetry is called scale invariance. Let's forget for the moment that it's broken at quantum level, but scale invariance is the thing which you can rescale the field x by some factor. You can rescale the field by some factor. Lagrangian will change, but the action won't. So the action is the integral over the Lagrangian density. So you can have the so-called transformation, which is called scale invariance. So it means like you are zooming in or zooming out. Okay, this is why it's called this scale transformation. So scale invariance. The only thing that would break scale invariance is the mass term. Okay. So in fact, it is true that in this Lagrangian, which I wrote down, if I send mass to 0, there is this scale invariance. However, remember that hidden assumption, okay, the hidden assumption is that there is a new physics scale lambda. So there is a new physics scale lambda. My hidden assumption breaks scale invariance. So maybe by this scale invariance, you can justify when I did a calculation only with the Higgs, why in the dimensional regularization, I don't have anything proportional to the, but when I introduced a field phi, a new heavy field phi, then I broke scale invariance because there is a, there is a particular scale I picked. There is a mass of phi. Okay, so my hidden assumption breaks scale invariance. So in fact, In fact, this statement is true, the one that I wrote in my lecture notes. No enhanced symmetry when m psi goes to 0. Well, sorry, when m goes to 0, because I implicitly assume that there is a new physics scale lambda. Is this clear?
It's clear. Just one question. So where does this new physics scale enter then, if we say there is this?
Well, I don't know this. I'm just assuming that there is a new scale. And if there is a new scale, for example, it means that the Lagrangian will have a term which is m square phi square.
Ah, okay, okay.
So this m phi breaks scale invariance.
Okay, okay, okay.
And then it means if I send small phi m, the mass of the Higgs, to 0, I don't restore, the symmetry is not enhanced because scale invariance is now broken by this other piece.
Yeah, okay, okay, now it's clear. Thank you.
Okay. Usually the elementary scalar has no protection, provided that there is a new physics scale which breaks the scale invariance. Okay? That is the hierarchy problem. Now I will show you one interesting example that we actually observe in the experiment. And I think it's a very instructive example. I think it's the most striking example when you talk about the hierarchy problem. So please pay attention here, and if you don't understand something, please interrupt me at any point. So I will talk about the pions of QCD. Pions are the lowest, the lightest resonances of QCD. They are composite particles. So let's assume that our colliders are not in fact advanced, that we only got up to the energy of 0.2 electron volt. So imagine LHC has an energy of 0.2 giga electron volt, okay? We are doing collisions at that energy, so we found 3 particles, which are pi 0, a neutral pion, and then pi plus and pi minus, which are electrically charged. We measure their mass, and we see that one guy is 135 GeV, and the other guy is 140 GeV. So when you see something like this, you have a triplet. It's wise to assume that there is some global symmetry, global SU2. They are close in mass, so they are part of some multiplet. They are packed together, I mean, some multiplet. And they are triplet of SU2. We postulate this. Triplet of SU2 means that it's an adjoint representation of SU2. It's a real, adjoint is a real representation. So we write down the Lagrangian. There is the kinetic piece, and there is the mass term, and then there are interactions. What kind of symmetries can we have in here? We can have the so-called the shift symmetry. The shift symmetry is the symmetry of the Goldstone bosons. So the Goldstone boson are usually the lightest scalars. They come from they are so if you have a spontaneous symmetry breaking, then you have massless modes, which correspond to the broken generator. These are called Goldstone bosons. It's and they have the so-called shift symmetry. The shift symmetry means that you can change the field in a way that you have a field plus some constant, okay? You can shift the field. And the shift symmetry is, for example, preserved by this term because the derivative, when it acts on the constant, it gives 0, okay? So it's, but note that shift symmetry is not respected by the mass term. The mass term breaks the shift symmetry. However, imagine that interactions preserve the shift symmetry, that everything else preserves this so-called shift symmetry. We will talk more about Goldstone bosons in Composite Higgs lectures. And I send the mass to 0. Okay, I say m goes to 0. Then the symmetry gets enhanced. Okay, so m would be a technically natural parameter in that case. indeed, it turns out we learned that strong interactions respect the symmetry, okay? Pion is really a Goldstone boson of strong dynamics of QCD. Strong interactions respect the symmetry. If there were only strong interactions, pions would be massless and radiative corrections would not lift its mass, okay? However, this is not the case in nature. In nature, there are also electromagnetic interactions, okay? And electromagnetic interactions, they break the shift symmetry. So so this is the interaction between a photon and pi plus and pi minus. Okay, so this second term. And this breaks the shift symmetry. Not only the shift symmetry, it breaks also the global SU2, where we treat together pions and pi 0 and pi plus. So the global SU2 is also broken because now we treat pi 0 and pi plus differently, okay? So QED breaks both the shift symmetry and the global symmetry of QCD. Chiral Symmetry, so-called, okay, let me call it just global symmetry for the moment. So what do we expect? So meaning that there is this new interaction which breaks shift symmetry, that means that the mass parameter is no longer technically natural. Fine. So we expect quadratic corrections. And second, because we broke SU2 symmetry, so the SU2 symmetry is now broken, now we expect that we have a mass splitting. If the symmetry exact, the triplet would have the same mass. When it's broken, there is a mass splitting. So perhaps this contribution can actually explain this small difference in masses. And it turns out to be the case. So now we expect, now we will have a radiative correction to pi plus pi minus mass term, which goes as so there is this electromagnetic constant over the loop factor, and then there is some new physics scale, lambda. All right? So if we ask that radiative corrections do not overshoot m pi, okay? So if we ask radiative corrections not to overshoot m pi, then we can put upper limit on lambda. This is like some argument of naturalness, saying that we don't want to tune. We don't want radiative corrections to be bigger than the observed mass. It's very arbitrary, but from there we can get, because we know the electromagnetic constant, we know the mass of the pion from experiment, we can put an upper limit on lambda. So the lambda should be roughly smaller than 800 GeV. Indeed, when we crank up the energy, we see QCD resonances. In particular, the vector resonance m rho related to this problem is about 770 GeV. You can even calculate. M rho is the spin 1 cousin of pion. Rho is the spin 1 cousin of pions. So you can even calculate the mass splitting with these lightest, putting in the contribution from the lightest QCD resonances, which are rho and A1. A1 is the axial vector, and this is the result. You can calculate the contribution. So you are giving only the QED corrections give only contribution to the charged component, pi plus and pi minus, as you can see here. Okay. So there will be a mass difference between pi plus, pi minus, and pi 0. And you can see that this cancels roughly because MA1 is much bigger than M rho. So you see that the difference in mass is proportional quadratically to the mass of rho. Okay, and then there is this logarithm, and this agrees with the you measure the mass of rho, you put in this formula, and this agrees. So quadratic corrections are really there. So this really is, I mean, this is measured. This really is there in nature. It's a way to understand the mass splitting of the charged pion and the neutral pion. So QCD completes the low energy pion theory eventually, as anticipated by the pion hierarchy problem. So if you were a physicist where you only had those low energies, and you could say, okay, we have this pi hierarchy problem, so I expect new physics not to be far away. And indeed, you crank up the energy and there is QCD. Okay. At very short distances, pions are composite. So there are no elementary scalars anymore. They are made up of fermions, and that is the solution of the hierarchy problem in the context of pion. Are there any questions about pions? Was this clear? Yes, no?
Just a comment. The masses should be MEV, not GeV, right?
Sorry? The mass of what?
Of the pions.
Oh, yeah, absolutely. I'm sorry about that. Okay, I will change this in my notes.
Thank you.
Okay, let me put 0.1. Yeah, I'm really sorry about this. Right. Okay. Yeah, I think this is a very instructive example to understand really the hierarchy problem. So now if you do analogous exercise for the Higgs, then you have the dominant contribution comes from the top quark. You can do this exercise yourself, and you will see that you expect the quadratic correction to the mass of the Higgs proportional to the Yukawa top squared, which Yukawa top is order 1, and there is a loop factor. And then if you say that this radiative correction if you require it not to overshoot the Higgs mass, okay, the mu square parameter, then you get this bound of 500 GeV. And the big question for the Higgs is, where is everyone? Atlas and CMS did not find any particles so far. Some particles are ruled out up to several TeV. Yeah, it's a big question. Where is everyone? Okay, so this is the end of the first part. I will now switch to the second part, which will basically just be the summary of what I said here. Okay.
I have another question.
Yes, please go ahead.
Sorry. Given the current measurements, what would be the amount of fine-tuning that is required to get what we observe? Right.
To answer this question, you have to pick a model, okay? And for example, if you do the model which is very close to QCD, it's not exactly QCD, but it's very close to it, the so-called composite Higgs models, then tuning there already from the fact that we didn't find these particles is at the level of %, meaning that radiative corrections are about 100 times bigger than what you expect than the observed mass. So this is what we call today the little hierarchy problem. Okay.
And this order of magnitude is the same for, or is the least fine-tuning that is required in all?
It is not the least fine-tuning. I will talk about this in Composite Higgs. There are tricks called, for example, collective symmetry breaking, where you can make this tuning much better. You can make it to order 1. So that there are some mechanisms which you can implement on top of the, let's say, Composite Higgs to make this a little bit better. Analogous things also exist in supersymmetry. But then there is a question of, we will discuss this at length, like when you introduce these additional stuff, then you have more cumbersome models. Yeah, and then, at some point there is the question of,
Thank you.
It's a complicated model versus tuning some parameters anyways. All right, so this will really be just a summary of what I just said, but maybe the written notes were a bit confusing. So hierarchy problem is one of the most interesting problems when you go beyond the standard model that you have to address. In the standard model, the Higgs mass parameter receives at one loop corrections from Yukawa couplings, so from gauge interactions as well as from self interactions. So basically, all the interactions of the Higgs give you the quadratic dependence. So this diagram is the Yukawa interaction. The most important one is from the top quark. This diagram here is, for example, gauge interactions. Hence, you have this dependence on the electroweak gauge coupling G and G prime. Okay, and also this is the self interaction. So all interactions of the Higgs, it's quite generic. This problem gives you the mu square is this parameter here. Will depend quadratically on the mass. Okay. There are two terms which we call, for example, the little hierarchy. Meaning that, for example, if the new physics scale is at 10 TeV, and after that, if the problem is solved at 10 TeV, you have the little hierarchy problem. It's exactly the situation that we were talking about. And the big hierarchy problem would be if there is a desert up to M Planck. Little and big is quite obvious. In one case, you have a smaller tuning. In the other case, you have a horrendous tuning. So the question, so the problem really exists only if you have new physics, if you have a heavy state. Remember, we did this example where we said maybe this regulator, so we did in different regularization schemes, but we always got the dependence on the mass of the heavy state, which you could not remove. So this is the example when something new is coupled to the Higgs directly. So you get typically contribution at one loop. But in some models, you can have something which is coupled to something coupled to Higgs. For example, imagine you have some new heavy fermion psi, which has a mass m psi. And this fermion is not coupled directly to the Higgs, but perhaps it has electroweak interactions. Maybe it's let's say it's a doublet of SU2. It's charged under standard model gauge group. If it's charged, then it will via W interactions, for instance, talk to the Higgs, because Higgs is coupled to W and W is coupled to this guy. Of course, this is a two-loop effect, but still the effect is proportional to the square of the mass. So this thing better not be at the gut scale, 10 to 15 GeV, because you have a huge problem. You see how generic this it's very easy to destabilize the Higgs potential, the Higgs mass. Okay, so again, it's not about the regulator. As in any good effective theory, lambda in our calculation stands for the physical mass threshold at which new particle appears. So the hierarchy problem is the sensitivity to new scales. If there is no new scale, then there is no hierarchy problem. Okay, so we know that there are at least two. There are at least two issues that will force us to extend the standard model. The first issue is the appearance of quantum gravity around the Planck scale. And the second issue is the Landau pole of the hypercharge gauge coupling. So the hypercharge gauge coupling grows big, and at some point, although it's a very, very large scale, much, much bigger than the Planck scale, it's a sort of academic issue, but we know that standard model is not valid at all energies. Okay, there is a Landau pole which has to be cured. It can be cured by, for example, unification, gauge unification, where the couplings get unified to a non-abelian gauge group, which is then asymptotically free. That's one example of how you. But it definitely requires new physics. So hierarchy problem exists only if there is a new physics scale. So let me now tell you the Wilsonian formulation of the hierarchy problem. Remember that Wilsonian formulation had to do with the renormalization group and effective field theories, the way we understand effective field theories. So the Higgs mass term is a relevant operator. Remember, relevant operator is dimension full. So H square, the coupling is dimension full. M square is dimension 2. The Higgs mass is the only relevant operator in the standard model. The other operators are marginal. So as we go to infrared, meaning to low energies, in the RG flow, relevant operators grow. Okay, they get enhanced. So the formulation of the hierarchy problem is that it's difficult to choose the RG trajectory, which in the infrared flows to the correct Higgs mass. So if you know, do you have these RG trajectories in the space of parameters? So you take any model and you have couplings, for instance, and the trajectories in this space would represent the RG flow. Okay, so if you start at high energies, the hierarchy problem in Wilsonian formulation translates in the fact that you really have to pick very carefully the initial point, okay, in the parameter space in such a way to hit the trajectory which will run in the infrared to a small Higgs mass. Most of the trajectories will miss the light Higgs mass, and the immense tuning is needed to hit the right mass parameter. Okay. All right. So what are the most common solutions proposed in the literature so far? Actually, this question was one of the driving questions of beyond the standard model physics in last decades, in last 40 years, let's say. It got only, let me tell you, with the discovery of the Higgs, it only got even more profound. So now we know that there is a scalar which looks elementary. Its couplings are like expected in the standard model, and we haven't found any signs of any of those solutions which I am. So the mystery just got even worse, even more profound. So supersymmetry is one very appealing candidate for when going beyond the standard model. It's a symmetry between fermions and bosons. So it will be a symmetry. The transformation of the symmetry will change a fermion to boson, etc. It will put them in the same multiplets. Okay. Then the standard model Higgs will have its fermionic partner called Higgsino, which is a fermion. And the chiral symmetry, which protects this fermion, will also protect the Higgs itself. Okay, that is the idea. So the boson will be bound. Elementary boson will be bound to the fermion, and the fermion is already protected by chiral symmetry. So supersymmetry is some extension of the space-time symmetry. That's one idea, to do the extension of the space-time symmetry. And we will discuss about supersymmetry in the next lecture. The second popular class of models are called composite Higgs. In composite Higgs, Higgs is actually not an elementary scalar. It's a bound state. Composite Higgs is basically similar to this pions in QCD. Higgs is a pion of new strongly interacting dynamics. Pion meaning Goldstone boson, and this explains why we first saw the Higgs and not the other resonances from new strong dynamics at the TeV scale. Composite Higgs is another very, very interesting and mainstream approach to address this problem. The third approach, somewhat related to the second one, are called warped extra dimensions. So you have an additional dimension where the scaling in this dimension sort of brings, there is this exponential scaling brings closer brings the scales together. And it's very interesting that it's been shown that this picture is dual to the composite Higgs. So composite Higgs and extra dimensions may be the two faces of the same physics. There are other more exotic ideas. For example, there are many different ideas, but some of the other notable exotic ideas are large extra dimensions, or relaxion or anthropic. For example, in relaxion idea, you are doing something very different from this setup. You rely on the evolution of the universe, and you say that from the beginning of the evolution of the universe, the Higgs parameter was scanned as the universe evolves. There was some relaxion field which you scan, and then once the Higgs mass change, Higgs parameter mu square changes the value, you trigger the electroweak symmetry breaking. So you were scanning mu going from large values to small, and once you cross the zero, at that point you trigger the electroweak symmetry breaking, and then there is a back reaction at which the scanning stops. So you somehow accidentally stay in the vacuum which seems to be tuned. So this is a very different idea, trying to sort of dynamically, through the evolution of the universe, understand the problem. This is a very recent idea, and there are no convincing models at the moment. And then there is anthropic argument, which is basically giving up on the problem, saying, well, okay, it's giving up on the problem. I don't want to go in more details about this. And just two final slides. The discovery of the Higgs mass of 125 was the dream case for the experimentalist. If you look at the prediction for the branching ratio in the standard model over the very wide range of masses, this was really the best place you could hope for. You have the most many channels opened with sizable branching ratio. So you can study the Higgs in many different ways. If it was heavier, if it was lighter, you would just see it maybe in one, or if, so for example, it was very heavy, you would see it in W, W, and Z channel, and the rest would be difficult, okay? So for the experimentalists, this was the dream case. But for theorists, it is a nightmare. First of all, in the standard model, if you take the standard model as it is and then extrapolate to the Planck scale, you can see that we live in a metastable universe. So standard model is valid. It can be consistently extrapolated to M Planck with this value of the Higgs mass. Okay. On the other hand, if you assume there is supersymmetry would like Higgs to be lighter. Then, but also this there is a pressure for it to be lighter, but also the mass that we measured is kind of okay. In the composite Higgs, it's a very different situation. Composite Higgs wants the Higgs to be heavier, but this value that is observed is kind of okay. If the measured Higgs mass was not this one, and it would make our life a bit easier, now it's a maximal confusion. And therefore, in this class, you have to study both supersymmetry and composite Higgs. Okay, thank you. If there are any questions, I'm happy to take it. Any questions?
Perhaps I have a small question. So the other ideas you showed on the slide before, I think, the more exotic ideas, they work for all kind of Higgs masses, or do they work better for the Higgs mass that we actually observed?
Well, these ideas are not very sensitive to the Higgs mass if you change it by 100 GeV or as for example, supersymmetry and composite Higgs. Okay. Supersymmetry and composite Higgs are very restrictive in that sense. They are very predictive. Okay, but these other ideas are not. Yeah.
And these ranges that you show for composite Higgs and supersymmetry, do they assume some kind of small, how's it called again? So does it assume some small fine tuning?
Yes. Right.
So there's a supersymmetry could go much higher if we assume that it's more fine tuned.
Of course, yes. This assumes this has a tuning argument in itself. Of course. These bands, if you allow for more tuning, they expand more.
Okay, thanks.
So we will discuss the solution to the hierarchy problem in supersymmetry and composite Higgs in the next lectures when we talk about these two ideas.